hope everyone is doing well. So in this video, I will briefly kind of talk about transformer model, in a positive sequence system, like how to construct it based on test data. So let's assume we have, let's see, so we have a single phase transformer rated 240 primary, 120 volt secondary, 150 kVA, VA. Then the primary DC resistance, so this is DC, is 8 ohms, and the secondary DC, resistance, again it's DC, it's 2 ohms. So let's assume you perform the open circuit test on the 120 volt side or the low side. So open circuit voltage is 120 volts, excitation current is 0.11 amps, no load losses is 6.9 watts, and the reactive power measured during this test, open circuit test, is 11 VARs. Then short circuit test voltage is 5.9 volts. Short circuit current, circulating during that test is 1.29 amps. Losses incurred during short circuit test is 6.5 watts, and VARs 3.9 VARs. So we want to create the model from this, and this is really a test that manufacturer will perform, and that's how they would come up with basically like the core losses, load losses, and also the impedance, provided this is a small transformer, but the same thing can be applied to any transformer basically. And I'm picking single phase just to make it kind of, because the focus is more on the concepts, because once you understand the concepts, you can apply them to three phase easily. So, we have DC resistances here on the primary and secondary side. So we assume this is a true two-winding transformer. And by that, I mean it's not an auto transformer. So the high side and low side, or the primary and secondary, they are not physically connected. So if we assume this is the primary side, so this is the 240 volt side, and this is the secondary side, 120 volt side. So then for the resistance, basically you connect the ohm meter basically across the leads of the primary, and the ohm meter basically will apply some voltage and it will measure some current. So then the resistance basically on this side is just voltage divided by current. It's Ohm's law basically, and you apply DC, so you apply DC basically voltage. So the same thing, you do the same thing for the secondary side. So what you do, you can use the same ohm meter basically. So these are the two leads, one start finish, for instance. You connect them to the ohm meter, then you will apply some voltage. You will apply some voltage, which is DC. Then current will flow, DC current, and basically the resistance on this side, which is DC, is just the voltage that's applied divided by the current that's flowing. So that's how you would perform the resistance test basically. So for the open circuit test, again, let me get the red color here. So again, you have the windings. So let's assume this is the 240 volt side. This is the 120 volt side. So for the open circuit test, you only apply the test to one side. For a small transformer, you can apply the test on either side. For large transformers, in the kV size, like 34 kV to 12 kV, for instance, or even transmission, like 345 kV to 138 kV. Typically, the open circuit test is applied on the low voltage side. It's for safety purposes, and also manufacturers may not have the capability of applying a higher voltage. So for our purposes, let's assume both voltages are, we can supply them. And the other thing is 240. If you are in a lab, for instance, you may not have 240. You might only have 120, or 208 volts, for instance. So those are the limitations. But just it doesn't matter which side you apply the voltage to, you will still get the same results. So let's just pick one, for instance. Let's assume we're going to apply the voltage on 240 volt. So basically what you do, you have the source here, AC source. So you apply 200 volts AC. Then you leave the other side open circuited. So this here will cause some current, which will be very small, as we saw from the test data. It's very small. Some current will flow basically, and that's the excitation current. So in here what we do, and then you can measure both, so have a voltmeter, for instance, connected here. You can have an ammeter to measure that current. So basically that's how you do the open circuit test. So now for the short circuit test, again we have the same transformer here. So here's the 240 volt side, and here's the 120 volt side. So for the short circuit test, for large transformers, typically it's applied, the short circuit test is applied on the side with the high voltage, because the side that has the high voltage will have a lower current. And it's for safety purposes, lower current, plus manufacturers, they may not have the capability of producing a high current. For a transmission, for instance, the low side might be rated 3000 amps. That's a lot, versus the high side might only be, say, like 900 amps. So 900 amps versus 3000, that's a big difference. So open circuit test typically is done on the side with the low voltage. Short circuit test typically done on the high side, or the side with the high voltage. For the purposes of what we're doing, let's assume we don't have an issue. We can apply it on the 240 volt side. So basically what you do, you connect the source, which is AC, and what you do, you circulate the rated current. So this current here, or let me take it back. Let me start with the setup first. So you energize, so you connect the source to one side. The other side basically is short circuited. You connect the terminals, you put a jumper or a conductor or a wire such that it completes the circuit. So now, then what you do, since I'm applying the source to the 240 volt, so then what you do, if we take 150 VA divided by 240, that's 0.625 amps. So you apply AC voltage until you circulate a rated current. In this case, it's 0.625 amps. Then you stop. So then what you do, so you measure this voltage that's applied, then, and you have an ammeter which will tell you when you reach the rated current. And the same thing, if you happen to apply the test from the 120 volt side, basically you would just circulate twice the current because the ratio is 2. So 120 volt will have, side will have 2 times 0.25 amp, So it doesn't matter which side, it's just you will still get the same result. So basically that's the setup, and that's how you apply these tests. So now from the test data, we can do some calculations to come up with the positive sequence circuit model of this transformer. So let's start with the shunt branch. So in the open circuit test, these are the values we measured. So the core resistance, so basically the shunt, so the primary will have, so if I call that P, RP, this is JXP, that's the impedance of the primary side. Then I call this RS, XS, JXS, which is the reactance of the secondary. This is just RS secondary. S means secondary. Then this is the core resistance, and I'm just drawing per phase just to make it simple. So this is JX and magnetization. So when we applied the open circuit test, current flow in the secondary, IS, if I call it IS, was 0. If I go back to the setup here, because current here, since it's the circuit is open, the current will be 0. However, but I applied the test to this side here, primary for instance, so some current will flow through the RC, which means the core. So the transformer has a core which will have some losses. We'll represent that by RC. And also, to establish the magnetic field required for induction to work in the transformer, we have to provide magnetization. So XM will do that. So RC, this is if you apply the test on the secondary side, then it's just because in our test data we're told the test was applied on the 120 volt side, so it's the secondary. So then the equation is just V squared divided by P basically. NL just means no load, or open circuit test, basically what it really means. So 120 volt square divided by 6.9 watts. So I get 2087 ohms on the 120 volt side. As you can see, it's a very large. And you know, if you read textbooks or if you work in industry, you will realize that basically they just ignore this branch here because it's just too large. It acts like an open circuit. So it's an approximation to eliminate it, which is okay in some cases. In other cases, so it just depends on what you are doing. Now I can take that same RC that I calculated on the secondary side and I can refer it to the primary side. then I just use the ratio, basically 240 divided by 120 quantity squared, which is just 2 squared 4 times RC, which is 83. So on the secondary side, this is the value. On the primary side, so this is on the primary side, then that's the core resistance. Now the magnetization reactance on the secondary side, so V squared divided by Q, so I plug in the numbers, I get 1309 ohms. I can take this here and refer it to the primary side. So XM primary is 240 divided by 120, which is just 2 squared, which is 4 times 1309. So I get 5236 ohms. So I calculate the open or the shunt branch impedance. So now we can calculate the same thing for the series branch or impedance, series impedance. So from the short circuit, so from the test here, when you perform the short circuit test, unfortunately you cannot separate the primary resistance from the secondary resistance. You don't have a way to do that. So what you measure really is the total resistance or reactance, which includes the primary and secondary. So that's why I have in parentheses R primary plus R secondary, which is equal to P divided by I squared. Basically, all I'm doing is P is equal to I squared R. So if I solve for R, it's just P divided by I squared. And I'm just emphasizing that this is losses measured during the short circuit test, current measured during the short circuit test. So if I plug in the numbers, P is just 6.5 watts, current is 1.29 quantity squared. So I get 3.91 ohms on the secondary because the test was performed on the secondary. So that's something you want to kind of keep in mind. You want to use the values on which side you perform the test on. So then I can take that resistance and refer it to the primary side, which is just applying the voltage ratio, basically 240 divided by 120 quantity squared times 3.91 ohms. So I get 15.64 ohms on the primary side, which makes sense. The primary side typically will be larger than the secondary side. So that's one indication. If you get, say, like just hypothetically speaking, I made the calculation and I got 3.1 ohms, I know something is wrong. The primary typically should have a higher resistance than the secondary side. So this resistance here, which is the total, which includes the primary and secondary, is based on AC, measurement. I can use the DC. So the DC resistance, which is given here, which is measured using an ohm meter, basically, which is DC. I can take the primary, referring it to the secondary plus the secondary. Basically, I want to calculate it, refer to the secondary side. So I take the primary divided by the voltage ratio. That's what I'm doing here. Because the reason I'm doing this, because I want to refer it to the secondary side plus R secondary. So the primary is 8 divided by the ratio, which is 2 squared, which is 4. 8 plus 2, sorry, 8 divided by 4 is 2 plus 2 is 4. So that's on the secondary side. I can also refer it to the primary side. I can take the primary DC resistance, which is 8 ohms, then take the secondary resistance, which is 2 ohms, it's given, times the voltage ratio, which is 240 divided by 120, quantity squared, which is 2 squared. So 8 plus 8 is 16 ohms on the primary side. For smaller transformers, the resistance will be probably dominating the reactance. And by small transformers, I mean like distribution type. So I can do the same thing for reactance. Again, there is no way you can break this into primary and secondary. When you perform short circuit tests, you measure both, the sum of both, basically primary and secondary. So then the equation is I take Q divided by I squared, then I just plug in the numbers. So I get 2.34 ohms on the secondary side. I can refer that to the primary and I get 4.68 ohms. Again, we cannot measure X primary and X secondary separately. However, for the model, we can take this here and just split it by 2. Just assume X primary is equal to X secondary, then just divide by 2 basically. Now we will calculate the per unit values. So for the shunt branch, so we calculated RC on the secondary side, RC on the primary side, and here are my base values. Primary is 240 volts, secondary 120 volt, transformer is 150 VA. Those are base values. So then I know Z base, primary is the V primary squared divided by S base. Then I just plug in the numbers, I get 384 ohms. I do the same thing for the secondary side, I get 96 ohms. So then RC, or the core resistance on the primary side in per unit, I just plug in the numbers, so I get 21.74 per unit. That's on the primary side. Now on the secondary side, I plug in the numbers, I get 21.74. That means my math is checks, it's good. If that's the nice thing about per unit. In per unit, you don't have to worry about primary, secondary. You should get the same value. So if you calculated 21.74 per unit on the primary side, but here you got something like say 14 per unit, something is wrong. You should get the same value. We can do the same thing for the reactance, the magnetization reactance basically. So on the primary side, so XM primary divided by the base impedance. So I just plug in the numbers, I get 13.64 per unit. The same magnetization, except on the secondary side, I should get the same number basically in per unit. So that's the beauty about per unit. And that's one reason why engineers like per unit rather than actual units, because then you don't have to track, is it on the primary side, on the secondary side, what is the base, once you convert it to per unit, you don't have to worry about it. And if you want to go back to actual units, you know your base values, it's easy to do. So now we will calculate the per unit for the series impedance. So primary, we calculated the resistance is 3.91 ohms on the secondary side, and on the primary side we got 15.64 ohms, and we have the same base values. We have the same impedance base, or base impedance, primary and secondary. So then I take the resistance. So on the primary side in per unit, so I just plug the number, basically 15.64 divided by 384. I get 0.0407 per unit. Then if I perform the same calculation on the secondary side, I should get the same number, which is good. So I will do the same thing for reactance. So this is what I calculated for reactance, 2.34 ohms on the secondary side, and 9.36 ohms on the primary side. So then if I convert that to per unit, it's just plug in the numbers, I get 0.0244 per unit. So now one way we can represent on a per phase. So per phase basis model, that means I'm just assuming one phase. So again, I can do so this is RC. So RC is 21.74 per unit. This is JXM, which is 13.64 per unit. So this here, this is R primary. So what I can do, I can split, so I can call this R primary, RP primary. I can just take this number here and divide it by 2 basically. So basically 0.0407 divided by 2. And this guy here, J, X the primary. Again, we don't have a way to calculate the primary reactance and secondary reactance or even resistance. So we can make an assumption and just divide it by 2. So for reactance, I'm just going to take this guy and divide it by 2 basically. And do the same thing here. So RS secondary is equal to RP and JXS is equal to JXP. Another model, which is an approximate model, you can just do something like this. Like anything else, you need to know what you're assuming or how your assumption might affect your results. So here, what I can do, I can just put the entire resistance plus J 0.00244 per unit. And here, RC, here JXM. So instead of like dividing by 2, I can do that too, or I can put it on the other side, like you can move this branch, oops, you can move this branch here, this shunt branch, to this side, which is an approximation, so, but that's basically how you go from test data into creating the positive sequence circuit model of a transformer. Again, this was a small single phase transformer, but really you can, for a 3-phase, basically what you do, you calculate everything on a per phase basis, and the test is done similarly. Basically instead of having 1 phase, you have 3 phases. For open circuit, you leave the one side open, the other side you energize it. For short circuit test, basically you energize one side, the other side you short circuit all the terminals. Basically you take 3 terminals and you put a wire across all of them so they are short circuited. So it's the same test, so I might do a quick video on that, but I wanted to start with single phase since it's easier to demonstrate and easier to understand, and all right, have a good day. Thank you.